Members and friends to our PCS-IBS seminar. Today we have the pleasure of hosting Professor Viktor Kagalovsky from Shimon College of Engineering, Beersheba in Israel. And our scientific host today is Sergey, who will introduce Viktor.
Okay, so welcome everyone. It's a great pleasure to have Viktor Kagalovsky with us again. He's a frequent visitor to our center, and I guess I don't have to introduce him with too much detail, but let me just mention the main steps in his scientific career. He did his education at the Kharkiv Polytechnical Institute from 81 to 87, where he did his Bachelor and Master of Sciences in Physics of Metals and Semiconductors. And then he moved to the Ben Gurion University, where he finished his PhD in 1995 at the Ben Gurion University. And then he spent he had the time and postdoctoral positions at the Max Planck Institute for Kernphysik in Heidelberg. And he moved to the Shimon College of Engineering in Beersheba, where he is now full professor and dean of the Faculty of Engineering. And he did lots of work in disordered systems and electronic correlations. And today we are looking forward to learn something new about quantum scaling for the metal-insulator transition in a two-dimensional electron system. Let's welcome our speaker.
Okay. First of all, thank you, Sergey. Thank you very much for warm words and for approving my very late application in such a difficult year when I didn't know when my semester would start and when it would end. And okay, I'll tell a few words after my talk about this. As usual, I start by representing the place where we are all now, and the unknown flying object of my college. And this work was done in collaboration with Sergey Kravchenko, Dmitry Nemirovsky, and Igor Klurkevich, who is presenting here. And I will give you the general picture of the experiment, which already one of the main experiments for the last 30 years. It was done in 1995. Yeah. I'll tell you even the short history of how it was not accepted, finalized. Then I'll show you how we can numerically evaluate. A lot of things were already numerically evaluated at that time, 30 years ago, and then we can also improve some things. And then I would suggest that there is a chance to describe it as quantum phase transition, and I will make a proposition. We want to define particular effective action and to explain how it is being driven through the quantum phase transition. Then I'll talk about how our results really can represent the results of the experiment and the relation between correlation lengths, which you can calculate, and localization lengths, which can be measured in the experiment. And then finally, I'll show you that actually the picture, which was published also in 1996, of this experiment can actually be considered as a phase diagram in the density temperature plane, which is now very accepted description of the quantum phase transition. So first, the experiment. This experiment, this is one of the many papers devoted to it, and you can see that as function of the resistivity of two-dimensional system, strongly interacting two-dimensional system, can behave like a very definite insulator. When temperature goes to zero, the resistivity goes to infinity, or definitely like metal. The lower the temperature, the lower the resistivity. And there is this red line, which is almost untouched. It looks like this resistivity at this particular line doesn't feel the temperature. And the differences between these temperatures is just the density of electrons, which is changed by the gate voltage in a two-dimensional system.
What kind of material is it?
We will see in a second. And so first, it's against all the rules. Metal-insulator transition in two-dimensional system. But and so at first it wasn't accepted, and there were a lot of questions and stuff like this. And I'll show you now the pictures from the presentations which already have been done here by my friend Sergei Kravchenko, who is the author of this experiment. So first it was done in Kravchenko case, it was MOSFETs, if I remember correctly. Then it was done in silicon germanium, then in gallium arsenide system. And all this with years, there was a reproduction of this result. So in a lot of different two-dimensional systems, this different insulated and metallic behavior was observed. And as you can see by the names, when it comes to the Nobel Prize group, it's already much better. When it is published in PRL and in Science, it means that it has something. And the story tells that the day Philip Anderson said, there is something here, then everybody believed that there is something here. And this is the way how it developed. And obviously, you know all that by the definition of the Anderson localization, or by the definition of the Renorm group approach by the gang of four, there is no phase transition in the single particle system. So it was clear that if there is any chance that this is correct experiment, then it should be the interactions which drive it, and then you need some theory to explain. Yeah.
How about the correlations? If I have single particle, but there are correlations of the digital.
Very nice question. And as we discussed today, you know that almost everywhere in the two-dimensional system, it will be still localized. Now, if there is an external magnetic field, you have quantum Hall transition. So there is a transition, but this is not transition between insulator and metal, as in Anderson. The only, as I mentioned today, there is a very special case in two-dimensional systems, which is called D class. And in D class, indeed, it is allowed to have both insulating phase and conducting phase, metallic phase. So not just single line, which is a critical transition like in quantum Hall, plateaus. When you have plateaus, it's insulator. When you have steps between the plateaus, it's a critical state, and in temperature, it becomes a little bit wide. The only case which I know in two dimensions with non-interacting is D class, and D class is a description of very special islands of P superconductors, so not S wave, P wave superconductors, and you can have some extended states. So if you have a sea of, and in the sea you have islands of superconductors, then you have a chance that there will be percolation which will persist for some finite regime, but nothing more.
Yeah.
But this transition is transition to superconducting state or to...
No, not to superconducting. It's edge states. If you have an island of superconductor, there are edge states which are running around, and this is what will produce your extended states, not a superconductor. So it's excitations of the superconducting. But this is what we correct. But I did it 20 years ago. Yeah.
Yeah, but what I'm talking about, for example, if you take to O'Brien model, it will have a metal.
Okay, I'll accept it, but this is definitely not it. Okay, so obviously there were ideas by people how you can explain it. And I'm not saying that I will be talking to things in my explanation, but one of the great groups, the first one, obviously, if you can fix the Renorm group approach, and if you can observe metal-insulator in two dimensions, and obviously, in order to produce such a paper, it would be at least one from the gang of four. And it was done by Abrahams and his collaborators. So the idea was, you all know this famous picture. In one dimensions, everything below zero, everything is localized. In three dimensions, there is place where everything is delocalized, so this is a transition. For 2D, because this line was approaching, there were also very strong arguments that there is still localized, but the localization is so weak that maybe, so the idea of Abrahamson's group was to add to this famous D-2 additional term, which is positive, which will drive this line a little bit above, then it will still go from 0, but from above, and this would explain that you have a metallic phase here. This was one of the ideas.
Is there interaction here or not?
No interaction. So there was obviously
And even though the spin, no spin orbit,
spin orbit maybe, right? I don't, because this explanation didn't succeed. So I guess you are right. So there was some obviously addition you need to in order to produce such a term. Yes, please.
One consider Dye disorder?
No, I don't. No. Okay, and finally, obviously, there was a very strong approach. Unfortunately, it took too long time because I know some reasons and some misfortunes because of this long time. Postdoc wasn't printing very quick, and this was the production by Finkelstein and then time his postdoc Panos, and this was already a very strong approach, which now to be believed that there is an explanation. They constructed a real renorm group approach in the presence of electronic interactions, and they have shown that indeed they can stabilize a metallic phase and produce. Obviously, there were some assumptions. I'm not an expert on them, but one of the main assumptions was the infinite number of values, so you need infinite number of degrees of freedom to produce it. But this, at least, you see, according to the places where it was published, it was accepted as a really strong explanation. And since then, there were a lot of developments in this area. I'm talking about this particular group and these experiments by Kravchenko, and he reported it here that, for example, he observed what we believe is a Wigner crystal in the insulating phase, and in the insulating phase, his experiments were always accepted because everybody agrees that there is an insulator. There were a lot of interesting results and interesting publications. So this is the situation, and we wanted to look to it once again. So what was done once again in 1995? So if you take all the curves above this red one, and you want to scale them, they look very similar. And if you take all these curves in the metallic phase, you also want to scale them, and it turns out that this is one parameter scaling. And if you just divide this temperature by some parameter, which depends only on the density of electrons, they will all collapse to one curve, and all the metallic guys will collapse to the lower curve. And this parameter obviously is of the same units as temperature because you want to scale temperature. It's called T0, and it goes to 0 exactly at this critical density of electrons. And this looks very much like the transition, and I will cite one of the papers by Vlad Dobrosavlevich, who called it, this is the hallmark of quantum criticality. And we now are allowed to cite it because it really looks like second order of phase transition, something.
How do you get, so who produced this? You?
No. It was produced in this is the same picture.
No. Who found this T0?
People who are making Kravchenko paper.
It's fitting parameter. It's fitting parameter.
Fitting parameter. You play with numerics.
No, it's not a fitting. It's a fitting function, and
You're absolutely.
And how do you get it?
You're absolutely right. You're just there is a method which is called the least mean deviation. Yes?
I see.
And that's it. And they got it. It was very nice. Fantastically. You don't expect on the insulating phase and on the metallic phase, you don't expect them to have the same, it's the same exponent. It's one function. So it's a function which depends on n critical, obviously on n, and there is one parameter, and I will call it critical exponent. And
So
you can
no
see
explanation of this.
no, not explanation at all. But once again, I'm extremely honest, so I will show you everything was done many years ago, and then I will try to show what we are doing now.
So in this case, you assume that the density of this order is constant. You just check the density of.
Let me.
It's always the same. It's the
Yeah. Oh, okay. Very nice. This is the same system. You have one system, you know, two-dimensional electron graphs produced on the, let's say, between above you have metallic gates, and here you have this sandwich of semiconductors. Then you apply gate voltage, you change the number of electrons. You don't change the number. You don't change, you can call it still disorder. Okay, so we decided that we'll try to understand what is going on first, and I have a very nice collaborator, which is very good in the computers, Dima Nemirovsky. So first we used the most advanced computer, and we obviously reproduced the same values as was done with very old computers in '96. And we will have obtained the same T0 points. So first you obtain points, and then you scale them, Sergey, what you asked. So first you obtain just the numbers which you need to scale in, and then you fit some function. And we reproduced exactly the same result. And I'm very sorry for this poisonous color on the laptop. It looks okay, but I didn't. They told me to copy it. It's n. This is the density of electrons, and this minus the density of electrons at critical point. This point. And here is it goes to 0 with the critical exponent nu1, and I will show you that there will be nu2, which will hopefully they will agree between each other.
So wait, so you have an analytical approach to?
No, it's not analytical. Up to now, it's just numerics.
What did you do numerically?
We did exactly the same. We just repeated what they did. We didn't do anything new.
You repeated the fitting.
Yes, the fitting. We repeated the fitting, and we obtained exactly the same result. So,
Basically, just again a data analysis.
absolutely nothing new. It's definitely so. And this value was very interesting. It's 3/2. Sorry, we'll have next step. We were still going behind their results. And what they did in, let's say, 28 years ago, they took all the data which collapsed on the insulating phase, and they tried to fit already this resistivity. And they did it, and you see it looks like very exponential, stretched exponent. So they did it once again, 90-something, 98, and they obtained that all these curves, especially at low temperatures, can be described by this function, where temperature is in the denominator of the exponent. And here is another critical exponent alpha, and they found that this alpha is 1/2. And the moment they found it, obviously what they did, they just took the literature. Actually, I think he even called by phone to Boris Shklovsky, and because this is the result of Shklovsky and Frost. This is the explanations. Once again, by the way, I can cite people who are very nice, who were also not so convinced because the result of Frost and Shklovsky was a strongly interacting system, but they were actually considering one particle approximation. The interactions were taken into account by just by the words that there is a Coulomb gap in the spectrum. That's all. And they actually explained a lot of experiments, so I believe that they were correct. So this is the result of this experiment, and this was great news. So in the insulating regime, it produces something which is really insulator, and in 2 dimensions, it's really 1/2.
Frankly speaking, the agreement is only over 1 order of magnitude in temperature, right?
I would say 2 orders of magnitude.
No,
if I can start here.
No, you can't.
Okay. Okay.
So how bulletproof is all of you? Because fitting, you can convince yourself.
You're absolutely right. You can do whatever you want with numerics. No. I agree with you. I would say more. You can actually, we were here extremely honest, so we didn't go to, you can play, and if you play also with T0, you can actually make this curve, which there will be some finite errors. You can make it more, but I agree with you, it's okay, but I don't need it, so it's a,
what I guess I want to say is that it would be good to have more data to the left, so to extend this by one order of magnitude.
Yeah, no, but this is the smallest temperature. That's it. This is it. No, actually, here all the data was taken. I will be even more honest. On the next transparency, I will tell you that I'm not taking this data into account at all. Yes, please.
Yeah, as far as I remember, this Coulomb gap theory, it's variable range hopping between localized sites.
Yes.
It's random walk. It's not regular metal. Or
Nothing, but
it's a granular.
It's incredible, but it worked. But here already was very important point for us. Once again, it's 28 years old. And the point is the following, because when Frost and Shklovsky produced it, I remind you that they produced it for a single particle. They have shown that this parameter T0 is actually inversely proportional to the localization lengths. So this, if we believe that this is really variable range hopping, then it's experimental data which with numerics produce T0 actually allows us to think about localization lengths. And we can see that in this case, localization length diverges when the density of electrons approaches the critical one with the critical exponent, nu1. So this is on first point we did. Once again, it was obviously mentioned in the papers, but for us, it was the beginning. How can we think about something like this? So this is all data. Now, the very first numerics that we did. So once again, I will be extremely honest. We took not all the metallic data. We omitted data for very small temperatures. So if you remember the metallic data, I will show it many more times. It goes like this. And here it deviates. We wanted to see if we can describe at least the beginning of this behavior, how the metallic resistivity behaves when you decrease temperatures, but you are not at very low temperatures. So you see that here we're not going to zero. And this already was done for the very first time. And when we did it, we found something very, before that. So first of all, what we did, we also start thinking maybe there is kind of exponent, stretched exponent. So how can I check it? We took lambda of the resistivity on the metallic side, and we built, listen, log graph. So log graph of the log. So two logs on the left. And we found straight line that it was really good, at least here. And then if you have it, you start going back from log to the normal ones and from log to the exponent. And then it means that you can think about some kind of exponential behavior also on the metallic side. And this is what we have done. And we have substituted here, and this is our first result, numerical result, some stretched exponent gamma. And it turned out, once again, it was just ideas, nothing more than that. We don't have any theory on the metallic phase. On the insulation phase, we have Frost-Shklovsky, and also not 100% sure that this is correct. But here, nothing. But lucky for us, this new gamma became almost exactly 1 over nu, which was obtained in the experiment. Nothing, it's not nothing, but maybe it will help me later, I hope. So this was, yes.
It seems like at small temperatures, maybe the resistivity saturates because of disorder.
You're absolutely right. You're absolutely right. It sounds good here. And more than that, I'll tell you more. It's very interesting. Actually, in order to have metal, you don't need resistivity to go to zero. You actually can have also finite resistivity. But very interestingly, after we observed it, we found that actually there were experiments in 2 dimensions when people tried something like this, and they observed numerically. And once again, going back to Vlad Dobrosavlevich and his team, they, in the Hubbard model, they have found numerically that they can talk about exponential decay of resistivity in the metallic side.
So up to zero?
In Hubbard model,
Up to zero.
once again, it's very interesting because it's once again, we understand that if it will be non-interacting picture, we know that if we go to zero temperature, then through the time goes to infinity, and we should actually have this, but obviously not in the real system. Well, this is why I'm saying that we're not going to very low temperatures, but it was interesting. Okay, so now we started to think if there is a chance that we can write down some effective action that probably would lead us at least to some of the results. Once again, it's not RG by Finkelstein to Epanos. It's not our additions to RG by Abrahams. And so we went to the basics. And this is, as I say, it's not obviously not for people here, but if there would be some students, master degree or bachelor degree, this is a nice transparency about Landau.
Yes.
Maybe
before this, just out of curiosity, could you maybe in few words describe what was done by this by that group with RG and science paper? What was the idea of the RG approach?
No, I'm not capable to explain it. It's really, it's such a hard thing that, okay, the history tells that Aronov Altshuler, let's say 35 years ago, predicted that no interactions will never lead in two dimensions, that they only stabilize the insulator. Then Finkelstein studied the approach and found that there is some exceptions, that instead of, I'm afraid even to say, instead of the value, I don't remember if it was critical exponent or not, 2, he found that it's actually be 3 over 2, nothing to with 3 over 2 here. And then, no, he built, I think it was also, it was the diagrammatic approach.
So they had the field theory, including disorder, interaction, and they treated all coefficients. I mean, the interaction was described by 3 different parameters according to Landau categorization, and then they integrated out higher and higher energies, and all parameters they call it charges, like it should be in RG, and they have 4 or 5 charges. So all interaction parameters, disorder strengths, and one additional parameter, dynamical parameter Z. I don't remember. I don't remember the origin. So and also they had the arbitrary number of values. So just standard RG functional integral. You integrate out high and higher degrees of energy, but it was difficult to solve. I think they were solving it numerically because it was 5 or 6 charges.
Mm-hmm. Okay, so this is famous Landau functional. This is addition of fluctuations.
What is phi?
Phi is an order parameter, and obviously here it's Landau's theory. So I'm now showing a citation of Landau's theory. So phi is either magnetization, if we are talking about ferromagnet transition, or it is a mean bosonic field, like they called it later, but in a trivial way, it's a just gap function. If we are talking about superconductor metal transition, which is Ginzburg-Landau, and in this case, the main idea was that this parameter, the parameter is constant, and this parameter is linear in the temperature, and so it becomes negative at low temperatures and positive. And then you ask to minimize this without these fluctuations. So if you ask to minimize it, this is what you find, that there is no order parameter at high temperatures, and there is order parameter at low temperatures. Very nice. And then you obtain that this order parameter behaves like T minus T critical, and this how magnetization should depend on when you approach the transition. Next step, and here obviously can also talk about Landau, Ginzburg, or I can talk about Pokrovsky-Potoshinsky. And if you add here fluctuations, then you approach like your parameter is actually this constant plus some fluctuations. And there is a nice solution, because from here you can find that the Green's function of this equation is actually a correlation function of your order parameter. So you can obtain that for any dimension, and we're talking about 1, 2, 3 dimensions, this function decays as the exponent. And obviously this parameter as the exponent is called correlation length. And you can see that it is because, by the way, it's also not mentioned almost in any paper in the books, that actually this correlation length is on both sides. Also in the paramagnet, where there is nothing to fluctuate, we are talking about correlation of fluctuations. And it's exactly the same with the difference of a factor of 2. So, and you see that this correlation function diverges as the power minus 1 over 2. This is one of the most famous results in physics. And so if you want to move from the second order phase transition, which is driven by the temperature, and you want to think about quantum phase transition. So first of all, obviously the parameter which drives the transition, in this case you have seen, it's the density of electrons, not temperature. This is point number 1. Point number 2 is related, because there are already a lot of results for quantum phase transitions. They are very nice and very physical, but it is very difficult if you are talking about metal-insulator transition. For the case of metal-insulator transition, to define the order parameter, as you asked me, I answered you immediately. Ferromagnet, magnetization. Superconductor, gap function. For the metal-insulator transition, it is very difficult. And here I will also, I'm citing the papers by Vlad Dobrasinovich, and he found a very nice solution. He cited only one paper, 1958, because in 1958, when Anderson was describing metal-insulator transition, in his paper, he also was talking about what would be the order parameter. And the explanation is very simple and very nice. If you look at the local density of states on the metallic side and on the insulating side, you will not see too many differences, because because when you average, you have to see nothing. But if you look at the typical local density of states, it turns out that on the insulating side, it becomes distinct. If it's discrete, then it's 0. And on the metallic side, it becomes like a bell, and then its even average value is not 0. And I would find, once again, it's a citation from the Anderson paper, that because the escape time is inversely proportional to the typical local density of states, then this is explanation. In the localization regime, particle is localized. Escape time is infinity. So it is 1 over 0. On the metallic side, particle travels. So the escape time is finite. And this was the idea. And so this idea was used in these papers. And obviously, we also are talking about order parameter, which is typical local density of states. But lucky, I don't know, not lucky, but I don't use this order parameter. Because when I was answering about magnetization, you can measure it. This order parameter, I don't care too much, because I'm looking for the correlation lengths, and you will see it.
What is typical density of space? What is density of space? You say density of space and typical, local and typical. What is difference?
So it's a nice question. So if okay, let's have a look. If we have I would say that when we're talking that, okay, in a trivial way, let's think about this infinite well. And in the infinite well, obviously everything is localized, and you have just 1% of this range. So if you look and you write this is spectrum, you do the spectrum of delta functions. This is more or less what I was saying. Nothing more than that. So if the particle is localized, this was the words of Anderson, then its spectrum becomes discrete, and then it means that on average, okay, I'm not sure about the word. I mean, no, this is correct word, but I'm not sure that I can explain the word typical local density of state. So the number of discrete peaks, this is in the localized regime, and in the metal, it's a continuous function.
So what could call other parameter in this case? Final width of the spectrum?
No, I would say is the value, obviously, of the. Or you can say you can integrate this density of states and divide it by the
If something is
rate.
localized, it's definitely one level.
Yeah.
If electron can escape the width of this level, so density of states.
Probably.
Should
So I would say
this width should be other parameter.
or something like this. At least this was the rules. So if we just write down this, we have to write down the same functional which was written by Landau. But now, instead of temperature, we are talking about M, the density of electrons. And so, what we know before we start? We know, at least we have taken these results, that there is localization length on the insulating sides, which diverges with this one, and this is definitely not 1/2.
Sorry.
Yes.
Here I think it's
Yeah.
in Landau theory, if you take into account fluctuations, you want to either have 1/2. So maybe because of fluctuations, you can divide.
No, just a second.
Just the question that you here compare the two numbers, but for Landau 5-force theory, you will also won't have 1/2 when you.
You're absolutely right. Obviously, close to the transition, the fluctuations are so big. I'm talking about the case. Okay, if you ask, because obviously we will ask this question, I don't know what would be Ginzburg criterion for our theory. And you're absolutely right. Obviously, for paramagnet, you will not have this 1/2. But for superconductor, you have it. Why? Because Ginzburg criterion is extremely small. They were lucky, they got it, and it was measured 1/2. So obviously, you're absolutely right. If I will go to strong fluctuations, then this theory is not applicable, and I cannot make it. So I'm talking about mean field with small fluctuations.
Is that correct? Yes.
Okay, so what can we write down? We write down exactly the same formula, but now this parameter A, I have to write it down. So first of all, what is the difference in a trivial words? Well, it doesn't depend on temperature, it depends on the density of electrons. Second point, in all second order phase transitions, we know the lower the temperature, the order, the higher the temperature, no order. Here is exactly vice versa. It's very interesting. It's also very nice for PhD students to explain them this R ratio. This is the ratio between electron energy and Fermi energy, between interactions and kinetic energy. And you know that it is actually inversely proportional to the square root of the density of electrons. So the lower the density, the larger R, the stronger interactions, you are in the insulated regime. The higher the density, it's very strange to believe. The more electrons you have, the weaker they interact. Why? Because their kinetic energy goes much faster. So here we need to change the sign. It will be not T minus T critical, it will be N critical minus N. This is point number 1. And point number 2, because I want to believe that I can get this number of critical exponent, I will put it 3. So this is what we suggested. I have no proof for it, but we want to try what would happen if this coefficient depends on the cube of the electron density difference and not on the linear part. More than that, we were told that we are accepted completely. Obviously, if I believe that Ginzburg criterion is small and my results produce something which are really experiment, you can still play with those two numbers. You can also have dependence here and you will still reproduce 3/2. We wanted to take the simplest possible model I'm using the words in the spirit of Landau's theory, but this is just exaggeration. Okay, so if we do like this, we repeat Landau approach, we get that at high electron densities in the metal, we have finite order parameter, and 0 we have in the insulated phase. And then we write down the same because we want a relation function. And now it's a nice picture. I don't know, maybe not for a PhD student, but for a master degree for sure. I enjoyed it. It's very nice that you can do it by hand. And also nice that Mathematica finally now produces correct results even for functions. So you want to solve this equation, you make Fourier transform, and you obtain this parameter. And I call it the correlation length to the power -2. And I will show you this is indeed correlation length. So how we do it? First, we substitute both values of phi naught here. And you see that actually you have correlation lengths both in the metallic and in the insulating regime. This is exactly the same formulas, and this is just twice larger here. They're obviously positive. And then next step, I want to go from the Fourier transform to the original function. So we make an inverse Fourier transform, which is obviously 2 steps. So the first integral is actually a Bessel function of the first kind of 0 order. And now you are left with the integration over decay. And this integration produces you a modified Bessel function of second time of 0 order. These are because 2 dimensions. In 3 dimensions, it would be just an exponent. So if you look at the asymptotic behavior of this K naught, it is indeed exponential decay. And this parameter is indeed in the ratio, in the denominator, so it's correlation function. And it turns out that this correlation function diverges with exactly 3/2. Once again, as long as it is applicable for this description. So at least for us, it was a good sign where on the insulating part, because once again, if I believe that if Kagalovsky was applicable to the experiment, then the experiment produced that localization, this T naught, sorry for the color, I'm really sorry. So it produced new one, the critical exponent for the divergence of the localization length. So it was localization length. This approach produces correlation length, but on the insulating side, what is correlations? Particles are talking to each other in simple words. So if there is an insulating, on the insulating part. So at the particle which is localized, it cannot talk to the infinity. So localization and correlation, at least I believe that this is accepted approach. The correlation and localization are at least of the same order. And this, well, I would say this was first good news for us. We were glad that we got it. Okay, so point number 2. What can I think about the metallic side? Because no theory is there. I cannot say, and maybe I said the wrong words also about localization correlation, but here. So we decided that we can check what will be the behavior of how, if I have this critical density of electrons, you remember that the resistivity is constant. And then we wanted to check if we change this density of electrons a little bit and go to the metallic side, how far away we deviate. So we just decided that we calculate the conductivity. And we did the following approach. So we took the conductivity here, this formula, minus the conductivity, which is constant, y over rho naught. We made, this is already not for students, probably for the high school. And we obtain that this difference, at least for small deviations, is T naught to the power gamma. Remember this gamma from here? And remember that gamma was inversely proportional to nu1. So we obtained these results. And it doesn't say that we are right or we explain something, but at least emotionally, I know that for non-interacting system, conductivity is proportional to the density of electrons. So the difference between conductivity here and there is proportional to the difference of the density. Here, obviously, this is not the case. I understand that this is a strongly correlated system, but at least the idea that the change, small change in conductivity, is proportional to the small change in the electron density, for me, it was good on the metallic side, where n is larger than n critical. This was point number 2. Then there was, in some sense, the last point. We took a very nice book. It's really good book by Continentina about quantum scaling with very detailed explanations, very simple words. And we took there this phase diagram. This is a phase diagram for the Ising model in the transverse magnetic field. And for this case, the results are so simple. If you are at 0 temperature and you go for very strong H magnetic fields, you will destroy the ferromagnet and you will get, which is called here, gap state. Second point, if you go at 0 magnetic field, but you have Ising interaction, and you go by temperature, obviously you have Landau phase transition. So this is this one. Then there is this critical line, which is transition between ferromagnet and not, but there is more. First of all, if you are sitting exactly at the critical point, and here critical point was the ratio between magnetic field and Ising coupling constant, and the distance between your system and critical one was just simply h over j here minus h over j at the critical point. If you are sitting exactly at this point, your system doesn't feel temperature. You are exactly on quantum critical trajectory. And this is exactly, this reminds the red line in the experiment. Next point, the last point. There is also an additional line, which is called crossover line. And why it is called so? Because well below it and well above it, the magnetization of the system behaves completely different. And this line behaves exactly as Igor told you about this also dynamic critical exponent Z. So here is this line, temperature, goes as power of this critical distance to the power critical exponent like nu times Z. This was the last point. And then we started to think, can we find something like this in our approach in the experiment? And it turned out that I already have shown it to you. So this is important for me. This is exactly the same line, but this is T naught. It's not the temperature, and but here it's exactly the distance to the critical point, the electron density. And here there are 2 lines, and obviously don't be confused. This is not a critical transition line, because in the experiment there is no ferromagnet-paramagnet transition, but at least there are some changes. So let's have a look at it. Once again, sorry, this is the last bit color. So it's power nu 1. This is 3 over 2. Okay. So what if I draw this picture in the plane temperature and density of electrons? So let us have a look. So point number 1, and these are the curves T naught, and these curves, according to the previous transparency, should behave as nu 2 times Z. What is nu 2? Correlation critical exponent. Z is dynamic exponent, which is responsible for the time dependence, or if you want, of energy spectrum of your system. So look here. First of all, if I'm sitting exactly at critical point, you remember this was this horizontal line rho naught. So this is quantum critical trajectory, and I actually have for it I have easy explanation. Along this line, it doesn't matter for temperature for me. This is rho naught. This is the resistivity of the critical at the critical value of the electron density, which was produced 30 years ago in the experiment. Point number 2, I expect that these lines should behave like nu2 to the power z. And you remember, it was, in my case, it was just nu1. This was obtained by the experiment from the Efroslovsky approach. No, sorry, it's before Efroslovsky. It's when the collapse of the data. So this was a very important question, and I wouldn't say how thankful we are for the critique of our work, because what is Z in this case? And lucky for us, this experiment is going on for 30 years. In these 30 years, Sergei Kravchenko measured Z in this paper, and lucky for us, big people published it in Reviews of Modern Physics, a theoretical approach. And it turns out that because this system is strongly interacting, Z is not 2, as many people believe. Z is close to 1. This is exactly 1 in theoretical approach, and is found close to 1 in the experiment. So on the very same system. So if I substitute this 1 here, you immediately realize that actually from nu2 times Z, I'm coming back to nu1. So this picture, at least for me, looks like the quantum phase diagram. This is more or less my finite transparency. I'll show you, the conclusions. Just to be completely honest, once again, this idea was to explain these particular types of experiment. But if in the different two-dimensional experiments, and there are a lot of them, the people would be able to measure any kind of critical exponent from the experiment, I don't know, direct localization is probably impossible, maybe some correlations, then we believe that our approach can be applied, and maybe there will be not 3 over 2, and maybe even more. One more point about this, why it's applicable or not applicable. You can calculate Ginzburg criterion only if you have a microscopic model, and if you have BCS, then you can come and calculate and say that Ginzburg-Landau is applicable and produces correct critical exponents. Obviously, I cannot say it's here, and hopefully, I don't know, maybe one day it will be possible to prove that this was correct. So this is actually our conclusions, that we're talking about quantum phase transition in 2 dimensions, that we were able to say at least some words about the critical exponents for the localization and the resistivity. And the last transparency was this phase diagram. In some sense, I'm rather positive to it. Okay, thank you very much for your attention.
Okay, thank you very much, Vita, for this very exciting talk. There were lots of questions. We still have time for more.
Yes, in your Landau theory, you introduced the order parameter in the metallic phase, right? This order parameter, what is the meaning of this order parameter in the correspondence that when you compare this model with the Ising?
Okay, so once again, here, as I said, we cited Vlad Dobrasilevich, who cited Anderson paper 58, where the idea that the order parameter should be non-zero in the metallic phase and 0 in the insulating phase. And this is why I have chosen this typical local density of states, or simpler words, the continuity of the density of states and the peaks of the density of states. This is maximum which I can say. This is all I can say.
Okay, Robert, please. Just want to generally, how you yourself found your theory? Is it phenomenological?
Well, obviously, just I don't have justifications that I have written to you this cubic dependence, but because it's in a sense produces some experimental results.
So in order to classify experimental observation, you should suppose that there is some phase transition.
No. Experiment, in my opinion, this experiment shows phase transition. As I cited once again, Vlad this collapse of the data is a hallmark of quantum criticality. So in this case, I would say.
But you refuse to discuss what kind of, what is order parameter?
Once again, order parameter was more or less formal for me because I wanted to look for the correlation function of these correlations. But if I ask him if I can produce macroscopic, I can produce without question. And I'm sorry, I just see audience in Zoom, and I want to go to my next transparency because you are here. It's very important for me to say these words. I wanted to say that this is a great honor for me that there are people here in the audience here, and I see a person in Zoom who will contribute, because this is a picture of Sergei Gradescu and his wife Victoria, who were brutally murdered by the Hamas terrorists on October 7th. And now there are a lot of people from the original city of Sergei and Victoria, Kharkiv in Ukraine, which is also suffering now from other terrorists. And we are now working to publish a special issue of the Low Temperature Physics Journal, which will be devoted to him. And it is important for me very much. It's nice that it's already a proper person has left. So I wanted to say even a few more words. It will be a very special issue. Obviously, people will be speaking about physics, and I'm very proud that this physics will be also related to the to this place, because we planned with Dario Rossa, who was here many years, that we will publish our paper, which actually started here 2 years ago when we were doing deep learning of metal-insulator transition here. And we also asked people who will be writing, they can include personal words about Sergei at the end of the paper. It's not very accepted worldwide, but because it's our journal, we can allow ourselves whatever we do. Thank you so much. It's important for me to say.
Okay, thank you, Vita. No, wait. Thank you, Vita. And I think we still have questions from the Zoom by Amnon. Amnon, please go ahead if I understand correctly.
The Ginzburg-Landau theory is based on a Taylor expansion around the simple state without the order parameter. In such a Taylor expansion, you assume the simplest coefficients, which would be linear in n minus nc. How do you justify the cubic power of n minus nc? A simple Taylor expansion would have also a linear term.
Yeah, I accept every word you are saying. I obviously don't have any justification. The only reason we started with cubic because it was produced, we knew by trivial calculations it will produce us 3/2. This is the only justification. You're absolutely right. I cannot tell you that this first derivative, we obviously understand that there will be no second order term, but because of the symmetry. But the first order term, to explain why this derivative will go to 0, I obviously cannot talk. That's out of question.
The other question is, you obviously don't know the Ginzburg criterion theoretically for this theory. However, do the experiments show any crossover away from this Landau-like description when you fit the experimental data? You would expect very close to the transition to see some results of the fluctuations.
You are absolutely right, but actually, funny enough, this I would say that actually the fluctuations not fluctuations, deviations from the continuity were actually observed far away. If you look, let's have a look for this. Where is this? If we look at the famous results. Well, here. I don't think that they observed any something. You obviously expect some fluctuations here because this is very close to the transition. But I wouldn't say that there were strong fluctuations here. No. I understand what you are saying. They were not measuring correlations. So maybe if they will measure, maybe there will be something. I don't know. It's a nice thing to discuss and to talk to the experimentalists. Okay.
No, the resistance should also show some deviations from the mean field
No,
description.
but here it's very continuous functions. All the stuff, obviously all of the arguments against the experiments were here when there was deviation. But these are, okay, it's very, yes, probably here you're right. Here, very, very low temperatures, yes, there are some deviation. You're right. So I would expect that.
Okay, more, yes, please.
Yes, I have a question. You talked about zero magnetic field, but in 2D, for example, in metal phase with disorder, we know that there is a strong effect of magnetic resistivity when, like Cooper-Ron diagrams, they are suppressed by magnetic field. Do you have some insights about this problem and finite magnetic field applied to the system?
Oh, okay, yeah. Okay. As far as I remember, Kravchenko is obviously applying magnetic fields here. If I remember correctly, at very strong magnetic fields, he destroyed the transition, if I remember correctly. Point number two, he also used it to underline that here spin is very important. And spin was very important in the Finkelstein approach, if I remember correctly, at least it was given two more the degeneracy. What else? I don't think he ever produced here quantum Hall. I don't think so. But yeah, probably this is maximum which I can say. That the strong magnetic field destroys the transition. This I remember.
Robert? I wonder if fermionic nature of electron play any role in all these considerations.
Right, something like
mean
field theory. Obviously, I don't.
Interesting.
Right.
We need it.
No, you're right. If we would add here some spin orbit or something, but we don't.
Just Pauli principle or something, and it should definitely affect behavior of the electron in principle.
With the density related to the KM, this behavior is what larger density give a more large KF with the delays of the betterment.
But I can see, but they only need density of the electrons. It can be density of classical electrons.
Yeah, but the density is direct.
There is no Fermi energy here.
There is Fermi energy because in the definition of obviously not in the formulas, but you have the ratio between interactions and Fermi. This is R ratio.
For example, I don't remember, but in Shklovsky-Efros theory, there was not so much the Fermi nature of electron was explored, just hoping of electron between localized states and correlation.
You're right. Yeah.
There was no, because it was hoping, it's not band structure when you would populate that. So I wonder if you really.
Yeah, but it was hoping between field and empty states around Fermi energy. So they had it.
Yeah, they had a Coulomb gap.
Good. Amnon, there's another question.
The Efros-Shklovsky theory, of course, does not have a transition at zero temperature. Here we are looking for a transition at zero temperature. But my question is, did Finkelstein predict any exponents?
No. Exponents?
I think he did. He did.
And how does he compare to what you described?
Okay. More questions? If that's yes, you.
In the metallic state, the same as for both ion pair bigger limit. The both ion pair bigger.
What?
Both ion pair bigger.
Your firm, what? Your firm.
Ion pair bigger. Your theory?
Yes. What your
criterion, KFN. I don't know, but hopefully in the metallic case it should be much larger than 1. That's it. Okay.
More questions? If that's not the case, Victor is still with us for some time, so together also with Igor, so please feel free to discuss with them. Thank you, Victor.
Thank you very much.